Let me extend my welcome to the latest installment of the Underground Storage and Utilization Technical Committee's webinar series on the geomechanics of storage of all things underground. That includes solids, liquids, gases, hydrogen, petroleum products, crude, CO2, compressed air, nuclear waste, thermal energy storage. You name it, we do it. This technical committee is part of the American Rock Mechanics Association as one of its initiatives, and we sure are glad you're here. Our presenter today is Dr. Sergio Sarmiento. Sergio holds a Master of Science degree in Geological and Geophysical Oceanography from Texas A&M. He also holds a PhD in Geology from the University of Houston. Sergio has more than 20 years of professional experience in reservoir modeling for conventional, unconventional, and crystalline basement reservoirs with an emphasis on fracture and geomechanics modeling. This includes the interaction between the natural and hydraulic fractures and the dynamic calibration of multi-scale discrete fracture networks, DFNs. Sergio has worked extensively in modeling fractured reservoirs across assets in the Americas, the Middle East, and Asia. He's been involved in the use of novel technologies for the characterization of fractured outcrop analogs to more precisely determine the mineral composition and geometry of fracture networks from individual fracture forming events, and the effect of diagenesis on fracture distribution and reservoir permeability.
First of all, Richard, thank you for the introduction, and thank you to you and ARMA, the ARMA committee, for the invitation to give this webinar. And I would like to extend also my welcome and thank you to all the participants for your interest in listening some thoughts about fall halos. I know this is a very exciting topic and you guys for sure have dealt with them. And since this is such a diverse community of both in the underground storage, solving underground storage issues as well as reservoir production. So what a good way that we can integrate this knowledge of fall halos both for seal integrity and reservoir production. So not all fall halos are equal. And you know, when we talk about fall halos, talking about the reservoir production, typically that is a good news. And it is a good news because that means higher permeability. So great, we have a fall halo, we're gonna have higher permeability in our reservoir, good production. At the bottom, we see in red, not a good news when it comes to seal integrity, because we gotta stay, especially when we're talking about top cap rock seal integrity, as these fall halos certainly are going to compromise that seal. But the core of this talk is that maybe there is somewhere in between, and this is specifically to two particular examples that I would like, or case studies that I would like to share with you guys. So where do we start? We start always with assumptions. And assumptions are a good practice, certainly, because they are built up on the experience, the professional experience and knowledge. But sometimes those assumptions don't hold truth with the data. First of all, we assume fall halos to be symmetrical around the fault plane. That's an assumption. But that assumption also is constrained, assuming that that will be the case, to, in the case of simulation, when we talk about reservoir production, to the grid size. So depending on the grid size that is being used, that might be problematic in the sense that if the grid size is larger than the fall halo, is not going to be able to capture properly that flow. But there is a workaround, certainly, when we are talking about coupled stress flow models. And then we can do a meshing that is more geared towards the fault zone or fault planes, a finer meshing that is going to be coupled with a larger mesh of the matrix or rock matrix. And that is one way how that can be simulated, as well as the fluid along the fracture and fault halos themselves, or fault planes themselves, using diffusivity and transport by advection. You know, there are different methods for that, but that could be computationally expensive. So certainly there is also an assumption about how the full halo looks like. Are we going to make this particular full halo an aperture, an effective aperture? Or is this just the trend of the fall? Is it going to be uniform along the trajectory? Are there any fractures that perhaps do not follow the same orientation of the fall halos or the fall trend? And those are the assumptions that typically what I had seen is that the first assumption is assumed that it's all parallel to the fall plane, but we're going to see that is not always the case. But ultimately, the ground data is the dynamic data. And if we are in a seal integrity study, when the monitoring size at the surface, I mean, certainly will tell us how good of a seal that can be. And in terms of reservoir production, well-test data, history matching, usually in these areas where we are trying to model full halos, is going to likely force us to revise that fracture and full halo conceptual model, this geometrical conceptual model. So let's talk about that. Let's talk about when we talk about fall damage zones, and when we talk about fall halo zones, we got to start with these cartoons, and depending on what problem we're looking at. And I'm going to present on the left-hand side a case of a sedimentary sequence. And this is after the work of Ogata et al. 2014, where this is a sedimentary sequence of the Jurassic sandstones in the Western United States. So in this is a sequence of aquifers and aquitars, and there are three main types of fall halos and associated fracture corridors. The typical one that we will expect here, that is called the fall damage zone fracture corridor, where we have the fall plane, and the fall halo is symmetrical across the fall plane, and is symmetrical not only in terms of the distance, but all along the fall plane. But it's also, they propose that not only there are a fall halo associated to the fall plane, but also to the fall tip. And it's very interesting. We will get back to this example and how that is actually supported by data. And also the development of fracture corridors associated more to what is expected with curvature on top of the anticlines. So that is if we were to look at a sedimentary sequence. What about if we look on the right-hand side about a fractured basement crystalline rock, where basically here we have a full halo that runs along the fall plane and is going to change in width from the surface to depth, is going to decrease in width as part of this width is perhaps enhanced by, if this was a paleo high, by the weathering exposure that will increase the halo, or perhaps by other reasons. But as we move down deep, that fall width becomes smaller. So those are conceptual models. And let's take a look at other perspectives. So we talk about fall halos in terms of the fall size, but what about the fall type? That is going to change too as well. So if we have a fall halo, what kind of fall are we looking at? And this is a very interesting example of a work done by Farrell in 2008, and where they look at a normal faulting system in Central Texas, actually a series of outcrops in the Balcones fault system. And here in this graphic on the left, we have propagation versus displacement. And what happens is that they look at the thickness of the competent to the incompetent layers across the fault system. So when the competent layers, and this is the case for the Edwards aquifer, are much representative than the incompetent, they observe four widths, narrow four widths, number one. They observe a pretty fairly constant fault throw along the fault plane, which is quite different that in the same area and under the same fault normal systems, tensional systems, when the ratio of the incompetent layers, meaning shell, is higher than the competent layers. And this includes the Eagle 4 and the Buda limestone all together. And what is observed here is that the fault halo width is variable, number one. Number two, the throw of the fault halo is as well variable. So it's less of a symmetrical distribution. So that's quite interesting because on the right-hand side here, what we can see is, first of all, the fault damage zone is not symmetrical. Mechanical stratigraphy and the sequence of rocks can dictate how that fault halo is distributed for this particular example. And of course, there is variability in permeability. So think about, we have a well in a particular area where there is not much displacement. Not taking into account this heterogeneity of lithology, we can overestimate or underestimate the permeability in the case of production, because we will assume that the fault halo is uniform across the fault, and actually is not the case, as it is supported by this particular outcrop analogs. Let's move from a normal fault setting to a Stratigraphy setting, and this gets even more interesting. Okay, so on the left-hand side, we have the slip surface evolution of a strike slip fault system. This is the work done by Diagenesis and Aidin, 2007, both on the left and the right. And here, what they show is the distribution, or basically the progressive, first of all, segmentation of this strike slip system, where there is the development of different splays. And these splays are basically different generation of splays. As the displacement increases, we go from 1 centimeter to 1 meter to tens of meters. So in each of these stages, the displays change both in direction as well as in magnitude. And what we wind up in this particular model is when a fault damage zone or fault halo that is quite heterogeneous in two aspects, that not all along the fault system, which is the merge of all these segments that started as a segmentation when fracture initiation and propagation, not along the core, the fault core is not located all along the fault system, number one. And number two, that we observe a diverse orientation of fractures associated to this fault system along the fault plane in this strike slip system. So that's on the left. And on the right, this is a nice cartoon that they have developed where basically they combine the damage zone based exclusively on a slip distribution of individual segments that eventually they coalesce as the fault progression continues. And they combine that classification of a fault damage with the static stress distribution of tensional and contractional and extensional to have more of a fault damage zone that not only is not symmetrical along the fault trajectory, but certainly has a very important component, tip component. And this actually is a really nice observation, because in a study done by Sarmiento 28 et al. 2018. This is a strike-slip system. And there are different wells across this fault damage zone. And there is this clearly a difference in the fracture distribution within the damage zone at well 1 compared to well 2. What it shows that basically depending on both the progression of the slip and the development of the fracture orientation related to that particular segment, we are going to have a quite not necessarily uniform distribution in terms of orientation in that damage zone. So fault types are key as well, not only fault size. And talking about fault size, how big that fault zone of fault damage width is. I think that's the $1 million question, honestly, because depending on the scale, it's all about scale. If we use seismic to be able to infer, first of all, the fault halo width, we're going to go with the rule of thumb that the larger the fault, the larger the halo, which makes sense, certainly, because the larger the fault, the larger the damage. Okay, but the question is, a fault size, if we compare two fault sizes that occur in different host rocks, that is a different story. And there is quite a lot of studies that support that some of those the halo widths varied significantly. So another way that we can do it is if we were to have an anisotropic seismic survey, and we will be able to find out what are those velocity anisotropy directions that are more preferred. So that's one indirect way. But again, all depends of the data, the scale of our data, and the scale of the target. If the target is smaller, obviously we have to make some inferences. So the fault width, I mean, as part of building the fracture conceptual model, certainly all these sources are key to be able to determine the fault width. But ultimately, it's until we have data, we can work with data, and we can narrow these possibilities. So in this presentation, I'm going to share with you two cases. One case that is about a fracture crystalline basement reservoir and the fault halo associated to it, and what actually was assumed and what it happened was quite opposite. And the second will be a seal integrity. So let's talk about the sigma factor. This is very important because as a type 1 reservoir where pretty much the storage and the flow is associated to the fracture system in this crystalline basement reservoir, the sigma factor is key because the sigma factor relates the fluid flow between the metrics and the fractures. And this dates back, we look here in this cube, to the Warren and Root dual porosity model, where back in 1963, the volume is divided in fracture planes, or orthogonal fracture planes, very simplistic, only when two sets, but basically provides the basis to the calculation of the sigma factor. The more or the higher the fracture intensity, these cubes are going to be smaller, right? And if they are smaller, there's going to be more contact, more communication between the matrix and the fracture. So that's nice. So it makes sense that for this particular study, there is this well. And this well has, that is on the bottom left, bottom right, we see the distribution of the fault plane, the fault planes, the poles of the fault planes, and has a very high fracture intensity. It's above 5 fractures per meter P10 along the well for a subhorizontal well. So obviously higher fracture intensity, higher higher sigma factor, great well, right? No, a really bad well from the production point of view. So wow, the assumption that we're making here of the fracture conceptual model that, number one, we have a big fall, really large size fall, and there are a lot of fractures, so great well. So what happened? Well, let's take a look at the fractures. For this particular well, there are image logs that were acquired as well as core. So that was a great advantage because we can calibrate the image log interpretation. This is a resistivity-based borehole image log, like FMI. And the core analysis can calibrate these images. And 4 different types of fracture types were found. Aperture enhanced fractures, conductive fractures, partially filled fractures, and microfractures. Let's see what they tell us. The aperture enhanced fractures that we see here with this dark color, higher conductivity for this particular borehole image, are associated to aperture enhanced, diagenetic enhanced parts of the core influenced by hydrothermal enhancement and dissolution. So looking at the analysis of the core, definitely the hydrothermal events play a role on the fracture aperture and enhancing it. But are these the only? So if that is the case, this well would have been even better than just assuming a smaller aperture, right? Well, so why is that is not that great? Okay, let's take a look at the other fractures. Conductive fractures, they're good. These darker color conductive fractures on the image log. Looking at the sinusoids, we expect higher intensity, really good apertures. We have partially filled fractures in less proportion. Still, they potentially could be part of the connectivity system. And we have some microfractures. So definitely we have to filter this out because which are the fractures that matter? If there are fractures all over and there so more investigation needed to be done. And the reason why is because at the beginning, I will show you the final result, but based on the work by Sarmiento et al. 2018, if we were to take all the fracture intensity and we were to take all those fracture apertures, there was no match when the history match was run. And it didn't also hold the DST results and the well test data and interference data, interference well test. So the need be for the static model to be sent back and start to ask some questions. Okay, so definitely higher fracture intensity doesn't work. Let's see what happens when the fractures. So consideration of critical stress fractures, fractures under the current stress that might be more prone to be active or active by the stresses was done to filter part of the fractures, but something very important was observed. In this particular region, there were multiple tectonic events. And the tectonic events can be modeled through strain modeling and cumulative strain modeling. And there were some blocks within this area that were more, that have experienced multiple tectonic events, and others that experience less of the influence of those tectonic events. What it was observed after integrating data was that actually the blocks that experience more tectonic events produce more fractures, but then it was a good thing that they produce more fractures. But one of the possible explanations why the HELO model didn't work, and I will elaborate in a second about that, was because these fractures that were open by these early tectonic events were occluded, but hydrothermal fluids that reacted with the host rock and actually occluded that aperture and permeability. In other areas that didn't experience the higher influence of that tectonic event, what happens is that that primary porosity that was not the best overall in the area actually helped because there was not much occlusion. So this model here that we see based on that well is basically proves that the Halo model doesn't work. And let's see why, because we see these large areas that are faults, and this is the sigma value. So certainly we see that the higher sigma value is not only constrained along the fault plane or across the fault halo, number one. Second, when we look at, and of course, this has been calibrated dynamically, and that's how these results of this work is, are concluded, is that actually out of all the fractures, there are two categories: the primary fracture production and the background fracture production. And those are linked to the strain distribution of the field. They are linked to the critical stress fractures, which ones are critical stress, which ones are not critical stress. And in addition to the hydrothermal effect, diagenesis, for making those aperture larger or not. So at the end, we see a bimodal distribution here on the upper left of two regions. Some of them are along the fault halo, but you see the fault halo is not productive all along the fault plane. Fracture intensity, same story. In a way or another, this primary fracture intensity mirrors that. And the background fracture intensity is, as background, is a little bit more consistent, but it's still, I mean, it sustains, but it's not significant compared to the primary fracture production. And the permeability, obviously, we see that is not uniform along the fault halo. So the fault halo model as such did not work. And this is a workflow that was proposed on this published study. And in this workflow, what I think is important as a take-home message is that it was the dynamic data and the calibration and the simulation that allowed to start to filter out the fractures that matter. And then a question that is very important to us in terms of the fault halo is how big is the tank? Because if we remember here, the tank, as we have modeled, is quite wider at the top of the basement reservoir, and it becomes narrower as we go down. So how big is the tank? The tank, and that is going to also obviously the KH being a constant number or value based on the well-test interpretation, but those are questions that are important to also run uncertainties, not only in terms of the static model, the halo model, and the properties of the halo, but also in terms of the tank. I mean, because those are the questions that also help to narrow down the choices. Okay, so that is for the case of fractured basement reservoir. And there is the work done by Agara in 2014, and that is very interesting about seal integrity. So we go to the, we were discussing reservoir, we wanted to have a high permeability, higher production. Here is the opposite. It's a seal integrity issue. We want to stay away from any leak, especially when top seal. I'm referring to top seal. This is a picture, a photograph of a fracture corridor associated to a fault system, where this bleach area, all these bleach lineaments, are basically associated, according to the authors, Ogara and et al., to CO2, the reaction of CO2 on the host rock, which shows kind of a paleo fluid flow, and that there was no seal integrity in this aquitar sequence. And this gets more and more interesting because if we look on the left here, this is the same area. We see this bleach area all across this sequence. And making a zoom here between a aquitar or a seal, in this case, a seal shell layer, this bleach, this evidence of the leak of this fluid across a seal was observed. So that brings us to think about the model, the conceptual model of the fault tip. And it is important because in this particular case, what happened is that the shell was, or the aquitar in this case, was also affected by this corridor. And one of the reasons could be that whenever we're working on a particular case, we just end our modeling where the seismic resolution tells us that that's the depth of that fault plane. But it would be worth, especially depending on what the problem is, certainly in seal integrity, to run some scenarios when the fault tip, to start to ask ourselves questions about what about if there is a fault tip corridor? What will be the effects of that? And look at your chemistry. That is also very important. Look at the chemistry of the fluids and that reactive fluid flow that is so key in the study of fracture media. And that's part of the work done in Los Alamos and National Laboratory. And on the right-hand side, there is a work done by that group, by a paper by Makedonska, 2018. And here, what they have done is taking CO2, and they have simulated 2 reservoirs, one at the injecting the CO2 at the bottom reservoir, and having the CO2 flow through a fracture cap rock. This is a fracture cap rock. The difference is that in this particular simulation flow that they apply, the flow goes through the fracture planes. Actually, not through grid cells like typically will be done in reservoir modeling, but it goes along the fractures themselves. And as such, volumetric considerations can be done of volumetric considerations using the Voronoi principle. And this is the simulation, and this is theoretical, but important for us to know, 245 days roughly, and about 2 years after the injection point. So eventually, having monitoring size at the surface, it can be determined, what will be the velocity of the flow across a fracture cap rock. And now, it's important to also know how thick is the cap rock, because it might be connectivity in this case is key. As we see in this example, there is a nice connectivity because the fracture lengths are such and apertures that allow the connectivity and the communication. It might be that this shell is pretty thick. So if it is pretty thick, even though a fracture tip might be present as a corridor, might not be a big deal, because if it is large or thick enough, it might basically, the diffusivity movement will be such a low rate that it should not be a problem. Okay, so conclusions: higher fracture intensities are not always proportional to flow, and so it's very important to see that based on the basement sample. If these fractures are occluded, they are not good permeability highways. The width of the halos is key. And the width of the halos, not only based on the fault size, and we know that the fault halo, and for modeling purposes, we make it symmetrical just to start with, especially when we are doing simulation grid sizes. But in reality, the fault halo is never symmetrical. And the fault size not necessarily equates, depending on the host rock, with the width of the halo. Important to know the reactant transport chemistry that occurs between the host rock and the fault halo and the damaged zone. Quite key, because these hydrothermal fluids have an influence, as well as the stress path of deformation. As we see, a stress path of deformation also reactivates not only movement and perhaps the aperture of some of these discontinuities, although there is always that toggling between diagenesis and stresses, right? To see which one wins the race, so to speak, as far as keeping the apertures open. Dynamic data is ultimately our ground to validate and run uncertainties on these models and minimize uncertainty through surface monitoring sites, if we're talking about seal integrity issues, and obviously in reservoir, flow simulation, well test, production, and history match. Like always, start simple is best, and we just add levels of complexity. As you see, this example about the fracture basement reservoir is pretty complex, and the only way that it worked out was to start simple. And Diagenesis definitely needs to be accounted to calibrate the fault hole zone and the aperture porosity. In some instances, might be more important than others. All depends. I mean, we have good metrics, and we want reservoir production. Well, it's not as critical as if we are looking at seal integrity, where actually enhancement will be a problem. Okay, very good. So with that, I'm gonna open the floor for questions.
Sergio, thank you very much. And fascinating talk. I could ask you questions all day, but let's go ahead and hear from our participants.
Realize how the fluid interaction with the fracture corridors and fault halos seem to be a key component in seal integrity. Yes, it is not only about the fault, but it's about the fault system. So I think it's key that the fault halo is a halo, and as such, it's not uniform. It can have a core. The core could be a porosity enhancer or not, as well as the orientation of the fractures associated to that fault halo, if there were to be present, also might be different than the trend of the fault. So there is an issue, actually in a way good for connectivity, but for seal integrity will not be that good. Fracture networks may become very complex across scales. Do you consider small scale fractures in modeling and how to decide on the critical fracture length below which fractures are not modeled? That's a very good question, Wenshu. That is going to be determined by your grid cell size, because if the fractures, the small scale fractures, in those cases, and often in fracture work, go into the matrix, so they might be accounted as porosity rather than being part of the fracture system. But all depends on the grid simulation size. Small scale fractures are typically, not always, the tank, the storage. Whereas large scale fractures, and again, large is dependent on what we want to model and the detail and resolution of that model. So it's going to depend on that. Stephen asks, I was curious what you mean by sigma factor in a basement reservoir. Sigma is a dual porosity term. Are you just using it as a measure of block size? Yes, so the sigma factor here is using it exactly just to exemplify the relationship between intensity and flow or communication between the matrix and the fracture system. And now, with that being said, Stephen, in some of the iterations for that particular work, there were, in the multiple iterations, there were some realizations where let's call it the microfractures were used as one media, and the large fractures were used as a the dual media. So basically, instead of considering metrics, okay, what would be the storage of the microfractures by themselves, a storage of the microfractures combined with the matrix, and the large scale fractures. So that was part of the realization.
Let's go ahead and thank our speaker again. And I wonder, Sergio, if you may have some contact information or other material that you might share, please.
Sure. So thank you to all of you for your attendance. If you guys have any questions, I will be more than happy to continue the conversation with you guys. This is my contact information. This is my email. You can also draw me a line on, send me an email or message through LinkedIn, and just looking at my name. And what I'm gonna do is I'm going to take this presentation and sanitize few slides, and I'm gonna post it on my LinkedIn account, so for you guys to look at it. But by all means, just feel free to contact me if you would like to discuss more.
Thank you, Sergio. Do you have any closing thoughts now that we've
Sure, Richard. My closing thoughts is that this work actually took me through working with full halos and modeling full halos. Actually was, and it is, a learning experience, in the sense that no particular standard model or workflow seems to work unless that we look at the specifics of each of the assets or the areas that we're looking at. So host rocks tend to be ignored sometimes, and sequence like mechanical stratigraphy. So it's that combination. The key is the combination of mechanical stratigraphy and combined with Diagenesis, combined with the knowledge of the stress path through the area, and just knowing the type of faulting and tectonics, because that will also help to link, for instance, or narrow down the type of halo models.
Sergio, thank you.
Thank you. Thank you to everybody for your attendance. I really appreciate it.